Video, we're going to talk about the graphs of the sine and the cosine functions. And so let's go ahead and get started. What we've been doing previously was we've just been evaluating trig functions. For instance, when I found the sine, for instance, of the angle x equals 0, for instance, right? So the sine of alpha equals 0. When I found that, I just basically went to my unit circle, found the angle 0 radians, and I took the y-coordinate of that point, and that would be 0. For instance, if I did sine of pi over 2, I would go to my unit circle, find the angle corresponding to pi over 2 radians, the terminal side where intersection unit circle, find that y-coordinate, and that will be 1, right? Notice each time that I evaluated the trig function, I got one single output, right? So it is a function, right? When you think of a function, you think of one input corresponding or getting assigned to one and only one output. And so now what we're going to do is we're going to think about the trig functions graphically. So where x is going to be our input value and our y is going to be the output, that gives us that trig function, right? And so remember that our trig functions are evaluated looking at our unit circle. So our unit circle, we have 0 here, pi over 2 here, pi, 3 pi over 2, and then we get back to where we started at that unit circle at 2 pi. And so I'm going to use these values as my input value to help me get an idea of what the graph of my trig functions are going to look like. I know traditionally when we start graphing and we don't know what a function looks like, we use the numbers like -2, -1, 0, 1, and 2 in our table of values. We plug it into the function and we get some y values to help us plot ordered pairs. Well, since we're talking about angles here, I'm going to pick numbers that allow me to get all the way around the unit circle. So 0, pi over 2, pi, 3 pi over 2, and 2 pi are good angles. And so I'm going to plug those values into my sine function on the unit circle, the y-coordinate where the terminal side of those angles intersect the unit circle, and we're going to get the following y values. We did the first two over here, so sine of 0 is 0, so my output value is 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is -1, and sine of 2 pi is 0. So what we have here is a bunch of ordered pairs, right? And so I'm going to plot my ordered pairs, right? For instance, I get the point 0, 0. Oh, and notice here, my x-axis or my input values are the angle measures. I'm just going to say angles here. And the output values, a lot of time people call those the ratios. Normally, like 1 and 0 and -1 aren't necessarily ratios, but they can be written as a rational number. But they call them ratios because we usually have things like square root of 2 over 2 or square root of 3 over 2 or 1 over 2, which are all considered ratios. But I'm going to have my ratios or my y values or my outputs of the trig functions on my y-axis. They're my outputs, and my inputs are the angles. And so I'll go ahead and plot my point. The point 0, 0 is going through the origin. I go right pi over 2 and up 1, and I get to that second point. I get the point pi 0, 3 pi over 2, -1, and then 2 pi 0. All right, and what we're going to do is we're going to connect this with a smooth curve. If we were to actually pick more points, we'd see, now this graph is going to look a little weird, that our trig function, all right, I should have went through this point here. Let's actually, okay. Do that there. This is my trig function, and I have a graph here, right? Well, remember that we can go more than one revolution, right? So I can go beyond 2 pi, right? Notice my input axis is counting by pi over 2s, right? I'm going to show you a little trick here, right? If I count by pi over 2s, 0, pi over 2, this is 2 pi over 2, which reduces to pi. This is 3 pi over 2, 4 pi over 2, which reduces to 2 pi. Then I get 5 pi over 2, 6 pi over 2, which reduces to 3 pi, and then I have 7 pi over 2. Okay, and so this same thing is going to continue if I continue to graph, right? So I'm going to change the color here, even though it's the same graph. When I do the sine of pi over 2, I'm going to get 1 because pi over 2, if I subtract 2 pi from that, I get a coterminal angle, which is pi over 2. So I get the same value here. And you'll see that the same similar stuff happens here, right? And so my graph is going to continue. and I get a graph that looks like that, and it'll continue on the right. I can count on my x-axis or my horizontal axis in a similar manner. So we have negative pi over 2, negative 2 pi over 2, which is negative pi, negative 3 pi over 2, negative 4 pi over 2, which is negative 2 pi, negative 5 pi over 2, negative 6 pi over 2, which is negative 3 pi, and negative 7 pi over 2. And then I can continue to draw my graph. Again, I'm going to change colors here. Unfortunately, my computer is being a little slow, sorry. But I'm going to get the same pattern going on the left side of my graph. All right, and so my graph is going to continue. And basically, I have a function that looks like this. As you can see, the domain of this function is all real numbers. If we use interval notation, that's negative infinity to infinity. But the range of my function runs actually from the smallest y value is -1. The largest y value is 1. So it ranges from -1 to 1. That makes sense because we're on our unit circle. And if our unit circle is placed into our standard position in our xy plane, the largest any y value can be is 1, which is the radius of your unit circle. And so one of the things that we want to introduce is the fundamental cycle. This is the cycle or the part of the graph that's the most representative, right? Remember, our graph repeats itself. And so we're going to call that fundamental cycle the part of the graph that ranges from 0 to 2 pi. All right, all of this other stuff is just a repetition of what I saw between 0 and 2 pi. So I'm going to call that my fundamental cycle. All right, we can do a similar thing for our cosine function. We're going to use those same input values. And what we're going to see here is that we're going to get a 1 when we plug in 0, a 0, a -1, a 0, and a 1. And so when we graph that fundamental cycle of our cosine function, we're going to get a graph that goes through 0, 1, pi over 2, 0, pi -1, and that. And so my fundamental cycle, all right, I'm getting a little sloppy here. I do apologize. It's harder to write on the tablet that I'm using, but I get this here. And remember, we can continue notating our x-axis to include these same numbers here. So I'll let you do that on your own. And then when we do that, we're going to see that we're going to get, I'm going to not waste the time in this video to do that. So our graph is going to continue. It's going to continue over here. Again, you will notate or label your axes, your tick marks, using those same values that we did for the sine graph function. And we get a graph that looks something like that, all right? Again, our domain is from -infinity to infinity. Our range is from -1 to 1. And our fundamental cycle, just as was the case with the sine function, is going to run from 0 to 2 pi. All right? And then everything else is just a repetition of that fundamental cycle. And so let's talk about some of the properties. These two functions look very similar, right? My sine function just goes through the origin and it goes up and you have a sine wave. All right, my function goes through the point 0, 1 for my cosine function and then it goes down and then you have sort of a wave type scenario here, right? And so because these graphs look like waves, they're called sine waves. And since these waves repeat at regular intervals in the domain, we call these functions periodic functions, right? It repeats, and so it has a period, all right? The period, which is given here, is the smallest number a such that f of x equals f of x plus a, all right? And so our period for these functions is basically that length of that fundamental cycle, right? I said that our fundamental cycle ranges or goes from 0 to 2 pi for my cosine function and my sine function, and then your function starts to repeat itself, right? And so our period of our sine and cosine functions are 2 pi, and that's basically the length of your fundamental cycle. That's the smallest number that if I add that number to our functional value, I'm going to get the same, to our input value, we'll get the same functional value. For instance, if I have f of 0, what we're saying is that this is going to equal the same thing as f of 0 plus 2 pi. And so since our functions are sine or our function is cosine, right, we know that the sine of 0 is the exact same thing as the sine of 2 pi. Same thing happens for the cosine function. The cosine of 0 is the same exact thing as the cosine of 2 pi. And you can do that for any angle, right? If I didn't want to start at 0, I could say, oh, well, if this truly is my period, then the sine of pi over 4 has to be exactly the same thing as the sine of pi over 4 plus 2 pi. And pi over 4 plus 2 pi is 8 pi over 4, that's 9 pi over 4. And the reason for that is that you're going to get a coterminal angle. And because you get a coterminal angle by adding a multiple of 2 pi, that's going to be your period, 2 pi. All right. Another feature of these angles is what we call the amplitude. The amplitude of your sine waves is the absolute value of half the distance between the maximum and the minimum y-coordinate, right? So since your range always ranges from -1 to 1, 1 is your max value and -1 is your minimum, right? And so if I do half the distance, so 1/2, the absolute value of 1 minus a -1, we're going to get 1. And basically, your amplitude is the distance from the midline. All right, I'm going to define this. All right, this x-axis actually would be the midline. It kind of cuts our function in half, right? So part of our function is above, the other part is kind of equivalently or symmetrically below, but shifted, right? Reflected and shifted. This is the midline, and basically your amplitude basically gives you this distance from the midline to your max or from the midline to your minimum. That's 1 unit. That's what we call the amplitude. All right. Now this is information about the basic graphs of y equals sine of x and cosine of x. We also want to be able to do transformations of your general sine waves, right? And so we can have different transformations, and we've seen this before. However, we're going to add different transformations here. Okay. Notice this a is multiplied on the outside. I have a number subtracted from the x on the inside, and then I have a number b that's multiplied on the inside of our trig function. And then I have a number added on the outside of our trig function. All right, when I say inside, I mean the input, right? So this is our input, right? And then this A is outside of that, and that D is outside of that. So B and C are done to the input part of our function. So it usually affects horizontal stuff. So it'll be a horizontal shift or a horizontal stretch or compression. And since the A and the D are outside of the function, it's things that's done to your Y values. And so it's going to be a vertical stretch or shift. All right. And so A, again, is going to be a vertical stretch. That's the number multiplied on the outside of your function. And basically, the absolute value of A is the same thing as your amplitude. All right. B, we haven't talked about this, but this is eventually going to be multiplied by the x. And so whenever we have a number multiplied by the x on the input of our function, that is a horizontal stretch or a horizontal compression. So it's going to make your function look wider, or it's going to make it look thinner, right? It's stretched or compressed in a horizontal manner. All right. This thing B affects the period. All right. Now we're going to talk about that in just a second. So I'm going to skip over that and go to what the C does. The C is an addition or a subtraction from the x in the input of the function. And when that's in the input of the function, that usually represents a horizontal shift, right? Right? That's what we've already known before. But since we're in the case of trigonometric functions, especially sine waves, instead of calling it a horizontal shift, we call it a phase shift, This actually affects the fundamental cycle, which we're going to come to in just a second. And then that D is basically a vertical shift. And so you can use the properties, the transformations of functions that we learned before. We just have this extra horizontal stretch here. You can use that to help you graph these functions. What I'm going to do instead is I'm going to use table of values, all right? And this uh, comparison of what happens to your fundamental cycle is going to help us graph by using a table of values. And so if I had a basic graph of y equals sine of x and y equals cosine of x, we know that the fundamental cycle, say cycle or interval, it runs between 0 and 2 pi. This is what we know. The difference between these regular basic, by the way, these are new functions to add to your library of functions, all right? But the difference between these functions and these functions, all right, in relation to doing anything with the fundamental cycle has to do with everything horizontal, right? You're going to shift it left or right, all that stuff like that, right? That's going on in the input of our function. The difference is that we're replacing the x in these basic functions with b times the quantity x minus c. And so what I'm going to do is I'm going to replace the x in my original fundamental cycle with b times x minus c. In order to see what happens to my fundamental cycle, I'm going to solve this inequality. This is a compound inequality. I'm going to solve it for x. The first thing I'm going to do is I'm going to divide each of these pieces by b. All right, so 0 divided by b is 0. If I divide by b in the middle, the b's are going to cancel, and I'm going to be left with x minus c. And when I divide by b here, I'm going to get 2 pi over b. I have that extra little line there, sorry. If I want to completely isolate the c, I add c to each separate component. 0 plus c is c. X minus c plus c is just x. And then here I add c, and I'm going to write it as c plus 2 pi over b. So whereas when I had my basic sine and cosine functions, my fundamental cycle ran from 0 to 2 pi. When I have a function written this way, my fundamental cycle is going to run from c to c plus some number, all right? And that number is 2 pi over b. And so if I'm going to think about my fundamental interval or my fundamental cycle, I'm going to write it using that notation there. And so that C represents the horizontal shift, which is a phase shift. It affects the fundamental cycle. My new fundamental cycle is going to range from C to C plus 2 pi over B. Now, with this, we also see that our period has changed when we look at this. And this is where this vertical stretch comes into play. Our period is the length of the fundamental cycle. Well, if my fundamental cycle starts, let's think of a number line, right? I start at C and I end at C plus some number, then the length of this fundamental interval here is basically, if I subtract these two, I'm going to end up with 2 pi over b. So my new period is actually going to be given by 2 pi over b. So where the period here was just 2 pi, when I have my general sine and cosine functions, it's going to be 2 pi over b. Let's use this information and talk about how we can graph. What we're going to do when we have these general sine waves is we're going to rewrite them in this form here. A times sine of b times the quantity of x minus c as your input, and then plus b. What we're going to do is we're going to determine the amplitude, period, and phase shift. We're going to determine the fundamental cycle. We're going to divide the fundamental cycle into 4 sub-intervals of equal length, create a table of values using the endpoints of those sub-intervals as inputs, and then graph using all of that information. And so here we have y equals 2 times the cosine of 2x plus pi plus 1. What I want to do first is I want to rewrite it so that it looks like y equals a times the cosine b times the quantity x minus c plus d. That means what I'm going to do here is I'm going to factor out a 2 from both of these terms in our cosine function. And so if I look at that, I'm going to put a bracket here. It's just like having a parenthesis. I'm just using the bracket. If I factor out a 2 here, right, then what goes in this parenthesis is what I get when I divide both of these terms by 2. When I divide 2x by 2, I'm just going to get an x. And when I divide pi by 2, I get a pi over 2. And so we can see that our a is 2, our b is 2. Our C is a negative pi over 2. Remember, that would be a shift to the left, right? And so our phase shift is our C is going to be a negative 2. And then our D equals 1, right? And so if you want to use transformations of functions, I recommend that you work inside out. And so what I would do is I will start with the horizontals. This will be a horizontal compression. Then I would shift everything to the left, pi over 2 units. Then I do a vertical stretch by a factor of 2, and then I'll add 1, all right? Now, I know you guys are probably wondering why this is a horizontal shrinkage or a compression. When the value that you're multiplying your input value, your x's by inside of your function is larger than 1, it's actually a compression. And then if it's smaller than 1, like 1/2 or 1/3, then it's actually going to be a stretch, a horizontal stretch, all right? But I'll always start with those. Then I do my shift left or right, which is that left pi over 2. Then I do my vertical stretch by multiplying my y values by 2, and then I shift up 1. I'm not going to do that this method because sometimes people find it hard to do that horizontal stretch. So what we're going to do is we're going to go through this process. I'm going to find my amplitude. The amplitude really does, it's just a property. It doesn't really help you graph, but it's the absolute value of A, which is the same thing as your vertical stretch. And in this example, our A was 2, so our amplitude is 2. So this is a good way, this is useful for checking your graph at the end, making sure that from your midline to your maximum point is 2 units, and from your midline to your minimum point is 2 units. All right. What really is going to count is the things like your period. And so our period, when it's written in this form, is 2 pi over B. Our B was 2, so my period is going to be 2 pi over 2. And 2 pi over 2 is the same thing as pi. Our fundamental cycle, I skipped the phase shift. Our phase shift, remember that's a horizontal shift, right? And that is coming from C. And our C here is negative pi over 2. And from that, we can get our fundamental cycle, which always runs from C, from that shift horizontally, to the C plus 2 pi over B, which is our period, right? And so since our C was negative pi over 2, and our period was pi, our phase shift, fundamental cycle is from negative pi over 2 to negative pi over 2 plus pi is pi over 2. The usefulness of this is that now what we're going to do is we're going to take that fundamental cycle and we're going to divide it into 4 equal subintervals. And this is coming from, let's do some thoughts here. This is coming from the fact that for our sine and our cosine functions, we have 1, 2, 3, 4 equal subintervals of equal length. And they have 1, 2, 3, 4, 5 points that create that fundamental cycle, or those subintervals. And so basically what we're going to do is we're going to figure out these points for this general cosine function. And so for me to do that, we take our fundamental cycle and we know for a fact already that that fundamental cycle has a length that's equal to our period. And so if I'm dividing that into 4 equal subintervals, then each subinterval is our period divided by the number of subintervals we have, which is 4 equal units, right? So from negative pi over 2, this length here is pi over 4 units. This length here is pi over 4 units. This length here, pi over 4 units. And this length here is pi over 4 units. To actually get these values of our boundary points or endpoints on these subintervals, we just keep adding pi over 4 to the previous subinterval. So negative pi over 2 plus pi over 4 is negative pi over 4. Negative pi over 4 plus pi over 4 to get me to this one is 0. 0 plus pi over 4 is pi over 4. And pi over 4 plus pi over 4 is pi over 2. That's how I know that I selected these correctly, right? And so what we've basically done here is we found the values of x that does all of the stretching and shifting for us. So we've taken care of this inside part of our trig function. All right. Now, since we know that this is the case, you could do a vertical stretch, right? So I'm going to use these as my x coordinates, and I think about my regular trig functions, my regular cosine function, which has y values starting at 1, going to 0, going to -1, going to 0, and then going to 1. What I could do now is I could use these as my x values, or my input values, use the same y values as 1, 0, -1, 0, and 1, and I can do a vertical stretch by a factor of 2. That means multiplying all my y values by 2. So I'd get 2, 0, -2, 0, and 2. And then I shift up 1 unit because that's a vertical shift. So I add 1 to everything. So I'm going to get 3, 1, -1, 1, and 3. And that's going to give me the graph of my function. In fact, I'll be honest with you, that saves us a lot of time. So what I'm going to do is I'm just going to do that. Uh-oh. So y got 1, 2, 3. I have 0 here, so I'm going to count by negative. I'm going to count by power 4s on my x-axis. And so I'm going to have this is our original y values, right, for our cosine function. This is our vertical stretch, and this is our vertical shift. And so I know I have the point negative power over 2, 3, negative power over 4, 1, 0, -1, 1, 1, power over 2, 3. And then I can draw my cosine function. And it would continue that way. And there we go. Now, alternatively, what we could do is we can create a table of values. And I'm still going to show you this because some of you may find this helpful. All right, now it just requires you to evaluate your trig functions at a lot of points, right? So I'm going to use these x values that made up my fundamental cycle. I'm going to plug it into my original function, right? Y equals 2 cosine 2x plus pi plus 1. And so what happens here is I plug in negative power 2. And for x, I'm going to write a little bit. 2 times the cosine. Now notice this is negative power 2 times 2, which is going to be a negative pi. If I add pi to that, I get 0 plus 1. The cosine of 0 is 1. I multiply that by 2, add 1, I'm going to get 3. I can plug in negative power 4. And for x, I get 2 times the cosine. Negative power 4 times 2 is negative power 2, but if I add pi to that, I'm going to get a positive power 2. The cosine of power 2 is 0, so this whole term could become 0, and I'm going to get a 1 here. And you could continue, and you're going to see you're going to get a negative 1 here, 1 here, and you're going to get a 3. Then you have your ordered pairs, which are the same ordered pairs that you get here. All right? Notice your midline kind of cuts it in half. And you can see your vertical stretch or your amplitude is that 2. The distance here from 1 to 3, y equals 1 to y equals 3. And the distance between 1 and -1 is 2 units. And so that's how you can use your amplitude to help you graph, right? So either of these methods work for graphing. You can do a table of values, or you can, once you find out how to do your phase shift and your adjustment to your fundamental cycle, you can use your vertical stretch or compression and your vertical shifts up or down, and that can get you the graph of your trig function. So this concludes this video. We'll see you during the next one.